So hello, welcome to the new section for this course, Introduction to the Computer Systems Design. So in the past, we had been dealing with circuits based on combinational logic inputs or based on combinational logic. And during that time, if you remember, we primarily discussed about circuits where the output depended pretty much on the current inputs. So there was nothing from a previous state or some kind of a memory that was being considered as a part of our system, right? So this is a quick recap slides just to make sure that we have already gone through most of it, right? And it is going to use full for your division. So you can ignore the how logic gates are implemented. We did not cover this in this particular course. This was not covered. This was not covered, but in order to get a more holistic understanding, sometimes we also look into how these logic gates are implemented using transistors, but we will just take it for as an abstraction at this particular course. And we have already given you idea about how this Boolean algebra and combination and logic gates could be used together to create combinational logic. That part was covered in good details, I would say. And then we also looked into ways to minimize this combinational logic expressions. So on one hand, we understood that for a given truth table, how to find out, let's say, SOP or a POS expression, and followed by that we were kind of using those SOP expression or the collection of these mean terms to create a combinational logic circuit. Next, we saw that how can we use this SOP expression and minimize it. So sometimes, as we already, if we can recall, that SOP expression is not equal to the minimal expression. This is very important, minimal expression. So this is also going to be useful for the later part of this course, because anytime you are coming across a truth table, you require this knowledge. Often the SOP expression that you get, which is basically a collection of mean terms, needs to be more simplified further. Okay. So after that, we also looked into a bunch of common combinational logic blocks. Sometimes we do not make everything from scratch using gates, but we use, I would say, off-the-shelf components that includes some common like Lego blocks. That is what I would say. Like if you remember, we were using things like comparator circuits. So comparators. Then we had adders, right? Then we had multiplexers or demultiplexers, right? Similarly, we had encoders as well as decoders, right? I'm just writing the word D. Then we also had like half adders, full adders. Then we also had priority encoders, which is a variation of encoders, right? So these were some of the combinational logic blocks which could be used in designs. And sometimes we do not want to use just gates from the scratch and use these components which are sometimes available in an IC format. In an IC form factor, you can directly use a multiplexer IC and then it already has the logic implemented, or let's say a decoder IC. So the decoder already has a circuit for, let's say you have 4 inputs. It can give you all the 16 mean terms that are possible, right? So the decoder will give you all the 16 mean terms. So you do not have to from scratch create all the not and or and all this kind of logic is not required. Sometimes you just get hold of a decoder and the decoder gives you all the mean terms, and you mix and match those mean terms according to your requirement, pass them to an OR gate, right? And get whatever is your expected output from the truth table and so on. Okay. Sometimes for this SOP kind of expression, decoders are very useful. Okay. So this is what we have learned. So apart from that, we also got some kind of a an experience in the circuit verse, right? So we are using this circuit verse to create some of these logical circuits, and it is primarily important to test out circuits, right? Sometimes you create a circuit and you do not know whether the circuit really works or not, particularly for a more complicated circuit. It's very nice tool for validating your expected outputs with the for a given set of inputs, right? Whatever we call as functional specification, right? In the very initial part of the course, when we design these logic circuits, we told that there are two things that we should care for. One was the functional specification, the other one was timing specification. So functional specification makes sure that for a given set of inputs, you are getting a expected set of outputs. That input output mapping is called the functional specs. This is nothing but your truth table, and using circuit implementation you can also validate that. Okay, so this is really a nice tool. Okay, this is developed, it's open source, developed by students from IIIT Bangalore. So you can, if you want to have interest in software design, you can even contribute to this project, right, to make it better. So this is really a nice tool which you can, all of you can use and make use of that and learn your combinational circuit logic better. We can also use it for designing sequential logic, right? So till now we have learned how to use this circuit words for doing combinational logic. So that was all, right? So we had some theoretical idea. We also had some very minimal, but we did try out certain circuits in this website, in this web application. Okay, so now coming back to the actual content, this is what I just now said, is if you have a combinational circuit, the outputs depend only on the current input, right? There is no dependency on what happened in the circuit previously. As an example, adder, we have studied full adders, right? Even in an arithmetic and logical unit in a processor, you will basically have adders, right? So when you add A and B and the result is C, it has nothing to do with what kind of addition has taken place earlier, what was the output earlier. As an example, if you add 6 and 5, your output is 11, right? It is 11 irrespective of whether you have added 6 and 5 earlier or 6 and 8 earlier, doesn't matter, right? Whatever was your output earlier, it has nothing to do with your current output. Whereas in case of a sequential circuit, there is a intermediate storage element where the output is remembered. Okay, so we typically say that combinational circuits are memoryless circuits. This is something that you have to remember. Combinational circuits are memoryless, whereas in case of sequential circuits, these are called circuits with memory. Okay, so the output not only depends on the current input, but also depend on the past values of your outputs, which again depends on the past values of inputs, definitely, right? So this is a subtle change, right? And that is I won't say subtle, this is pretty stark change with respect to the difference in between a combinational logic circuit and a sequential logic circuit, right? So this is what we call sequential logic circuit, and we are basically trying to design circuits that store information, right? There is some way we have to remember what happened earlier. Okay, so if I am at time t0, I am giving some input to the circuit, I get an output at time t1, and again at time t2 I want to give a new set of inputs. I have to remember what happened at time t1 or what were the outputs at time t1. So as you can understand that we need a mechanism to have or integrate a way to store information in the circuit. It is intermediate information, maybe just the last state, but you have to find out a way to do that. Okay, so here I would, just to make the slide complete, I want to write that this is a memory element, or this is memory that remembers previous states. Okay, so states is kind of analogously with used with output also. Sometimes you might have multiple outputs, you can have an input output combination. This entire thing could define a state of a circuit. Okay, So what was the last state of the circuit, and when you give a new set of inputs, the circuit moves on to the next state. So typically in sequential logic circuits, we will use the word state a lot, right? So it could be case specific. We can define what exactly it means. So either it could be a collection of the different outputs that it has, or inputs plus outputs and so on. Okay. So here let us see that how can we start with designing an element which can store information. Okay. So we'll start with something which is very simple. Okay. And let us see what the how this particular piece of circuit may work. So as you can see, there are two inverters, right? There are two NOT gates, right? NOT gates are also called inverters. It inverts the signal. One becomes 0, 0 becomes 1. So let us say this configuration is presented to you, and there are these two cross coupled NOT gates, right? The output of the first NOT gate, right, is fed into the input of the second NOT gate, right? And the output of the next NOT gate is going to be fed to the input of the first NOT gate, right? I am deliberately choosing two colors. Okay. So now we can kind of argue what will happen, and for the outputs, if you see, we are basically expecting two outputs which are complements of each other. So if you are having one as Q, or Q is equal to 1 or logic high, the other one should be logic low or 0. Okay, and vice versa. So you can cross validate that. So if you have one, let's say let me use red here. So if I am using 1 here, so this entire line is going to be 1, this is going to be 1, and your output is going to be 0 here, right? And then this is again going to be 0 because this is the green line, right? This is the green line here. Okay, and again the output is going to be 1. So this is kind of stable. Okay, so similarly, if you use 0 as Q, nothing is going to change. So I'll just rub off what I had, just the names, right, and then replace 1 by zeros. Nothing will change. That is what I think you can observe. So in this case, if Q is equal to 0, this entire red line is going to look like a 0 because they are all connected together. So the input to L2 is now going to be 0, and this is now going to be 1. So I'll just use this green color. This is going to be 1. This is again going to be 1, and it inverts, it is going to be 0. So if Q is equal to 0, you can see that Q bar is going to be 1 and nobody complains, right? Things are stable. Although there is a cross coupling, but if it is 0 and the other one is 1, that is fine. And vice versa, if Q is equal to 1, Q bar is equal to 0, that is also fine. So it has these two stable states, either Q equal to 1 or Q equal to 0, which is exactly the figure that I interactively drew just now. Okay, so these are the two possible states of the circuit. Okay, now you can start assimilating the fact what is a state. In this particular case, there is no specific inputs. There is some value that is being sort of stored in the circuit. If the circuit is powered on and nobody disturbs the circuit, it is going to store whatever is the value of Q indefinitely, right? As you can see, suppose Q is initialized somehow, don't have to see how, or we will see how later. If this Q value is there, it is initialized to something, let's say 0, and the circuit is powered on, it will hold the value 0, or if it is 1, it will hold the value 1. Okay, so now the other thing is it has a third possible state, right, which is often we call it a transient state of the circuit, or metastable. It's some state where values oscillate. Okay, so state when both the outputs are oscillating between 0 and 1. So that is a funny situation where your outputs want to be changed from 0 to 1, if somebody wants to change that output from 0 to 1, in that case it can lead to a situation where the output starts fluctuating. Okay, so I can very easily kind of annotate the diagram that we already have. So suppose this is a stable state of the circuit where Q is equal to 0 and things are all stable and fine, right? So let's say this one becomes 1, right? So when this becomes 1 uh, suddenly, so this entire red line that we have, this is going to become 1, right? So immediately this will try to become 0, right? So there will be some oscillation because it was already set at 1, and when you put 1, this is going to try to write it to 0. Okay, and that will follow, right? Because now if it is written as 0 now, this is written as 0 now, this will again become 1, but originally it was being shifted from 0 to 1, right? So there is some amount of oscillation that might actually be present, and at the same time you might have oscillations in the data itself, right? Again, 1 can become 0, 0 can become 1. So in that kind of a case, because of this the way the signal propagates, there could be an oscillating stage. It is not stable. Okay, so 0 becomes 1 and again 1 becomes 0, but in the meantime things will change and become like kind of conflict with each other. Okay, so those are the situations when it might take some time to become stable, or there is a little bit this sometimes becomes a little bit out of control. So this is not useful without a control mechanism. Okay, so unless and until there is a proper way to set Q, this kind of a circuit is not very useful. Okay, it is fine that if a value of Q is chosen and somehow set, I did not mention how it is set, I said somehow set to 0 or 1, it will hold it. If you want to switch the value, that might actually cause some amount of oscillation in the circuit, but still there is no clear way or a control mechanism that how can I set the value of Q, because once I know how to set the value of Q, it is as if storing a bit of information in a circuit, right? Because this will start acting as a very simplistic storage element. Okay, so this is about the storage. Now let us see that what can be done, like how it is stored, information is stored. So we have to have a control mechanism for setting the value of Q. Okay, so this is I will not go into the details of this particular diagram anymore further than this slide. So this is typically called SRAM, or a static RAM, which is a basic block of memory. Okay, RAM stands for random access memory, and this is called SRAM, a static random access memory cell, which is going to store one bit of information. Okay, and this bit of information is going to be written basically overwriting the value of Q. Okay, so if you want to write the value of Q, this is how there is a control mechanism. You don't have to worry much about this word line or so on. So there is something called bit line. Okay, so if you think this bit line, this is a value that I want to write to this particular memory cell, which stores one bit of information. So this one stores this entire picture that you are seeing. It actually stores one bit of information. Okay, so bit line could be 0 or 1. Okay, and so this could be 0, right? If this one is being treated as Q, like just to make it analogous to the previous diagram, this is going to be bit line bar, which basically means it has to be Q bar. Okay, in that case it is going to be 1. And the other thing is there is a word line. Word line is a particular line that enables if you want to manipulate this particular bit or not, right? And this is basically a couple of transistors. These are called NMOS transistors. You don't have to know much about it here. So this is, you can think of, if I put the word line as an active line, this is going to enable this particular SRAM cell, otherwise it will be disabled. That is very simple, right? So just think that if the word line is 0, I am disabling it, so this is as if it is going to be cut out from the circuit. So if word line is 0, word line WL, if WL is equal to 0, WL is equal to 0, it's like as if your SRAM cell is isolated, right? In that case, it is going to hold the information, mind it, right? It is going to hold the information, but if you want to change it, you have to activate the word line. So in that case, if I want to make it active, WL is equal to 1. Same here, active WL is equal to 1. If WL is equal to 1, these transistors are going to act as a closed gate, right? The circuit is going to be complete, current can flow and so on. So basically then SRAM is going to be affected by the bit line. Okay. So this is how, as we have shown in the last slide, is the same thing. It's the same cross-coupled inverter, just that Q and QR is written now. So bit line, if I put this bit line as, let's say, 0, so this is, let's say, this is your value of Q. Okay, this becomes 0, and this is Q bar. This will become 1, or vice versa. If I want to write 1, then I have to write 1 in the bit line. So if I write 1 in the bit line, so this is your bit line, and this is the flow of information, and then in that case Q is going to be equal to 1, here Q equal to 0. Similarly, in case of bit line bar is equal to 0, this was equal to 1 earlier, and now Q bar is equal to 0. So as you can see, it's the same thing, whatever we have shown, just that the Q and Q bar was connected to this bit line, and bit line is something that is controlling your memory element. So this is 1 bit of storage, because I was talking about storage. So I just wanted to give a real example how a memory chip looks like, right? This is one kind of memory chip. Don't worry, there are many technologies starting from SRAM to DRAM to magnetic tapes or magnetic disks and so on, SSD, solid state drives and so on. But this is a specific example where I can show that using this cross-coupled inverters, you can actually store a bit. And not only store, I can retrieve the bit, I can also write the bit. Okay. So this is something that you should keep in your mind, that the cross-coupled inverters could be used to in this following fashion to store, read, write bits. Okay. So you have some idea of how to use these circuits as a storage element, because if you look at this slide, we were talking about a storage element. Okay. So this storage element could be an output from a previous circuit execution, and we want to store it somehow such that the next state is determined. Okay. So I can give you one example at this point in time so that it is no longer vague to you. So I will give you an example where the next state depends on the previous state, right? I gave you an example of an adder circuit where the next set of output has nothing to do with the previous set of outputs, right? If I add 3 plus 4 is equal to 7, next time I add 6 plus 9 equal to 15, 15 has nothing to do with 7. Okay, that was a pure combinational circuit. But what if you have a state, a current state that actually is dependent on the previous set of your outputs? Okay, one example, very simple example that all of you have come across is called a counter. Okay, what does a counter do? A counter counts numbers from, let's say, starting from 0, and it wants to go up to a certain bit width, right? Suppose you have a 3-bit counter. So if you, I'm just digressing a bit in this part of the slide. So suppose you have a 3-bit counter. A 3-bit counter will do what? It is going to count from 0, 0, 0 to 1, 1, 1. Again, going to wrap around, and this 0 stands for 0 and in decimal, and this stands for 7 in decimal, right? And it is going to count. So now if you ask me the question that what is the value of count at a certain point in time, I cannot say, right? It depends on what was the previous output. Okay. For an adder, that is not the case. If for an adder, if you ask me that what is the current output of the adder, I will ask you that please tell me your current inputs. Okay. Whereas for the counter, I have to tell you what was the previous output. Okay. So let's say at a certain point in time, you have an output of let's say 4, right? 4 is 100. So this 4 is dependent on what was the previous output. The previous output was 3011, which was 3. If you ask me what is the next output will not depend on 3. It will depend on the current output, which is 4. So 101. This is 5. Then 6, then 7. Again, it can go to 0 and so on. But now you could understand that what is the definition of a sequential circuit more concretely. Okay. So the current output or the next output depends on the current output, or the current output depends on the previous output, and this is a tangible example. There are many examples like this. We will go into much more details about how to design this kind of circuits, how to design these counters and so on. But this is just the surface. In a superficial way, I kind of told you an example where the state not only depends on the current inputs but also on the previous outputs. Okay. So now this was one way of storing elements, and coming back to the SRAM, storing bits, right? And we will also see a more conventional circuit where called this RS latch, which is also called reset set or set reset, depending on what books you are studying from.